4. You have one on each side. Every time you have an asymptote, there's always one more picture. So you gotta have a picture on the right and left side of it. That's something we need to realize. So that's where we have to get very good at substituting stuff in, plugging. And so, like the types of problems we're going to be looking at in the next couple of days, we're going to look at that worksheet. Okay. Questions with why I didn't graph that thing yesterday? I want to put that subnet position where we have to try to draw that because we had multiple asymptotes on that problem. Okay, we're going to come back to that problem. And then we're going to try to mix in what we did today and with these problems, find out more roots and all that good stuff.
Wait,
what do you think? It's capitalization.
what decapitalized?
It was honestly the hardest one we love that was just that both onto the cell.
True.
Okay, if you say like my,
But honestly, that's
What did I miss?
if you say like my and
the rest of the
You only capitalize
you only
and.
it and.
Like she just used just
You capitalize and later.
If you were here Wednesday, you'll be fine.
There was like 3 of them. Well, this is your last time with
Then all you do is uncapitalize. There's like 3 of them. Yeah, like all of them that have and are on them, start with mine. So I mean,
So you don't capitalize the and when there's a my thing.
yeah, if mine is in front of it, you don't.
What'd you say?
When you capitalize street.
Why did you capitalize what? Avenue? Only if it's with the street.
I'm not gonna lie to you guys. Schools
Oh,
have been
yeah.
last
So it's
couple
Elm
weeks.
Street.
like on there,
That's
so we
fine.
can have
That's
Main
fine.
Street
AC
like
comes before
47th.
BC comes out. So
47th Avenue.
AD
Number or
yeah, you
But-
go down like main
So 50 BC.
50 BC and then 80 the number.
Alright,
Capitalize 40.
Don't even think about saying it.
Yeah, if there's more products, then you have to shift it towards the reactants, so then it's equal. Yeah, because you want it to be equal. So it's just like equilibrium and cell, remember? It goes towards the one that's less. It goes towards the one that's less. So whichever one has more, you just shift towards the other one.
Yeah, I do.
Yeah, it's pretty dumb,
That's
actually.
pretty accurate, actually. Staff getting back into their normal routine for today.
Your last slide, which is third on the wall.
today now. Did anyone turn in their homework already?
No.
You will want to hold on to it.
Yeah,
So,
it's the last 4
So,
or whatever.
that's what we're going to talk
Yeah,
about.
I saw it.
That's
I had more
Okay,
had to know.
so have it out. Did anyone turn in like a day ago or anything like that? Okay, good. We need to talk about the last couple. The reason why, they're going to really, I want to save it for today. Number one, I want to see how many people are going to ask questions on it, to see what time we've actually started with. And number two, it works really well with stuff where we just started Wednesday. That's why we kind of waited. Okay, so I can kind of like, you can bridge the gap, like, how do I know certain problems and all that good stuff. Okay, Ms. Steffen's in here, she's just observing, so don't worry about it. She needs to learn how to do this stuff before 9th period, so she's with you. All right, so, all right, because she's taking over for me in 9th period when I do that, so this will be fun. All right, so, now, on the homework, I want to do one of the problems from 39 through 48, evens or odds. It doesn't really matter. Pick one of the problems you had for your homework, and if you don't have one, I'll pick one.
41.
41 or 43, what do we
Both.
have?
Oh, no, both.
Both of them were hard.
I didn't know how to do 43 either.
Let's do 43, because that was a choice and you didn't mind, so we're going to do 43. That was a good choice.
They're both-
All right, so they're both equally like challenging. What we're going to do, this process, you can also do the process for number 41. You can also do the process for 44. Okay, the same exact type of problem. I need somebody to read off what 43 was. Okay, read it off.
F of x equals x to the fourth minus 2x cubed plus x squared plus 12x plus 8.
Okay, all right. Agreed? Great. Okay. All right, so the first step, remember, our goal here is to figure out possible rational roots for this problem. What a rational root is, that's your x intercepts. Where does this graph hit the x-axis, right? Could it hit it at multiple spots? Potentially, how many spots could it hit it?
8.
I know, like, you're thinking about, like, how many numbers could possibly work, but how many times will this thing actually hit the x-axis? A possibility of total maximum, 4 spots. Now, how we know that? What's your highest degree? 4. Highest power is 4. There's 4 x-intercepts, potentially. Okay? Now, let's talk about if they're going to be positive, negatives, imaginaries, what numbers these x-intercepts can be. Okay? So, how we do this? We set up a little chart. This is that Descartes' rule of sign. Okay? We're going to check how many numbers could be positive roots, positive numbers. Nice whole numbers, right? Integers. Okay, so positive numbers. So what we do is we start on this problem. We start here. What is that number, by the way?
Positive 1.
Positive 1. And what you're going to do is you're going to bunny leap front to back and count how many times does it flip from positive to negative or negative to positive. You count how many times does it change signs. And you count with your fingers. So we start with a positive number. So how many times does it change? 1, 2, and then it stays the same. So it changed signs twice, correct? From positive to negative, negative to positive, switch twice. So that means there's 2 positive numbers that will work on this problem. Or go down by 2. 0. That's your combination. It's 2 or 0. Now, how you know that? It always go down by 2s. So let's say we counted how many sign changes there were, and let's say it changed 3 times. So you go with 3 and 1. So that's the idea. You always go down by 2s. So if it was 7, it would be 7, 5, 3, and 1. You go down by 2s every time. Okay, so that's how many positive numbers could potentially work on this problem that would be x-intercepts. Okay? Now we have to do negatives. How many negative numbers will work? So to do that, we have to do that symmetry test. Symmetry test is where you take your polynomial and you plug in your negative x's into it. Exact problem. Substituting in negative x to everything. Because we're checking how many are negative roots. So what we need to do first, let's simplify this polynomial with the negative x plugged in. So simplifying it means you just look at the power and see if the negative sign stays or cancels out. Okay, so with the power of 4, what happens to this negative sign? Cancels, right? Even powers cancel out the negative sign. What about here? The negative sign will stay because the power of 3 will keep the negative sign, right? So the negative sign will go to the outside and actually turn that to be positive 2x cubed, right? The negative sign will stay, it goes to the outside. Here, the x squared, the negative sign has what? Cancels. Because it's the power of 2, it cancels the negative sign. Here, it stays, and then the 8 in the back doesn't change because it's a constant, there's no x's on it. Okay, so now we do the exact same rule. Now that we've plugged in all the negative x's and we simplified it, we count how many times does the sign change from left to right. So right now this is a positive 1. And you bunny leave, and you count how many times does it change signs. It changed signs twice, because it stayed positive, so nothing. And right here it switched to negative, and then it switched back to positive. So that's 2 sign changes, going from left to right. So that means there's 2 negative numbers that could work, or 0. You always should have by 2. Now here's the problem. You have to make every combination of those numbers. These are your combinations you can make. 2s or 0s, 2s and 0s. You have to make every possible combination. So it could go 2, 2, some number, 0, 0, some number. It could go 2, 0, this could be these 2 numbers, or it could be 0, 2. That's every combination of 0s and 2s possible using those numbers. You have to make every possibility. Then, what you do for the last row, this last column here, is the imaginary roots. So maybe it doesn't hit the x-axis. You know, you look at the picture and maybe it did something way above the x-axis. It oscillated up and down. You know, it turned a couple times. But it never actually did cross the x-axis. That would be imaginary. It had potential to, but it actually didn't. All right. So, what should these rows add up to be? 4, because there was 4 possible roots on this problem. 4 times this thing could have hit the x-axis because of your highest degree, this thing. So when you add these up, what do these add up to be? 4. So that means there's 0 imaginary. All 4 are already taken. What do these add up to be? 0, so I need to make 4 imaginary on that, so that they add up to be 4 actual roots. Here, 2. These add up to be 2, so there's 2 imaginary left over because these have to add up to be 4 total. And the bottom row, 2. They have to add up to be 4. One of these rows is the correct one. One of these rows represents how many times it hits the x-axis. They could be positive 2 spots, could be negative 2 spots, you know, wherever those numbers are. What our goal is, now that we set up this chart, is to find what those actual roots are, right, where they cross. And this is the hard part, agreed? The chart's probably not the hard part. It's probably finding those X intercepts because it didn't factor real nice and clean. All right, so now going to what Pat, you were saying earlier. There were certain numbers that worked, right? You knew there was like 8 numbers we had to check. Because how do you check? You take the back number on your polynomial, which is the 8, and you take the front number on your polynomial, which is the 1. Right? So that's 8 and 1. Back number over the front number. And what you do is you break these up. I need all the factors of 8 and all the factors of 1. Yeah, 1, 2s, 4s, and 8s. Right? Those are all the factors of the number 8. All the factors of 1 is 1 and 1 and 1 and 1, right? There's no other combinations of numbers. And what we do is we make every combination using the top number over the bottom number. So now there's a couple numbers down here. We make every possible combination known to man. And they're always positive negatives. There's always 2. Because it didn't matter if it was positive or negative numbers. Because they're potential roots. So what's 1 over 1? 1. Right? What's 2 over 1? 2. What's 4 over 1? And 8 over 1. So does everyone see that there's 8 numbers we're going to have to check? These numbers, what you're looking at here, these are the numbers that it could hit the x-axis. The rational numbers. The nice whole numbers, fractions, where I can hit the x-axis. Now, here's the bad news. I have no idea which numbers it's going to be. Because when you look at your chart over there, the chart didn't like glaringly tell me that maybe no negative numbers work. Because there was options, right? There was 2s and 0s and stuff. It wasn't like, I think there was one of your problems you had where the negative numbers, there was like 1s here. There was 1. So you knew that one of the negative numbers had to work. There was no other combination, right? It was just 1 the whole time. So, what I would have done on that problem is check the negatives first, because I know one of them had to work. But this one, there was options where it could have been 2 or 0, or so I need to check these numbers out. So what number should you always start with? 1. And how we check? You take the number 1, the positive 1 here, because that's the first number we're going to check, and you substitute it into your equation by doing normal substitution rule, and you see, does that give you 0? So when I plug in the 1 into my polynomial, it's 1 to the 4th power. Is that a minus sign? Minus 2 times 1 cubed plus 1 squared plus 12 times 1 plus 8. Right? So that's my original polynomial. We're substituting in the number 1, and what we're checking for, does this thing give me 0? So that's 1 minus 2 plus 1 plus 12 plus 8. There is no way that thing's giving me 0. Now number we check? Absolutely, we check in -1. We're going to plug the negative signs on it now. And this is where your calculator is really helpful. And I want to see, does this give me 0? And sure enough, it does. It will give me 0 when I actually plug a -1. Because that'll be a 1, that'll be that'll be a +2, +1, -12, +8. And these numbers here add up to be 12, and then you're going to subtract those. So it does give you 0. So that was an actual X intercept.
So when they plug it in the calculator, they're just typing
They're typing
the
that whole polynomial
there's
with
no like
parentheses
shortcut, they're just
every.
doing that whole thing.
Yep. And if you use parentheses, what they can do is they can bring it back up on their calculator, right, by hitting like the up arrows or like re-entry, and then they can just change the number and hit enter again. So it's like quick 3-second checks. They can type in all 8 numbers really fast to figure out which ones work. Now, we did find one that works, correct? So what should I do with that one number that we know works? Divide it out. We have to divide this root out, because what will happen if I divide out the -1, because we know it works, it should give me the rest of the roots that are left over, and hopefully, pray to God, it's factored. So, we're going to take out the -1. So by dividing, we're doing syntactic division. So the syntactic division, by dividing out the -1, you're using your leading numbers out front. Right? So the leading numbers on that polynomial is 1, -2, 1, 12, and 8. And we're going to divide it out. So here's how synthetic division works. You drop the first number down. So this first number drops down. And again, we're taking out the -1. That's because we know it works. So you drop the first number down. You multiply by the number in the box. That number by the number in the box. You add straight down. You multiply by the number in the box. You add straight down. You multiply by the number in the box. You add straight down. You multiply by the number in the box. And sure enough, it gave me a remainder of 0. So by dividing that out, this is your remaining polynomial right here. This is the rest of my roots. So this is what it represents. 8 plus 4x plus -3x squared plus x cubed. Because it's those are my leading numbers out front of those are remaining polynomials. Now, is this thing factorable? No. And that was probably the most difficult part about this problem. This thing was not factorable by grouping method. So, because if you grouping method, you were taking a 4 out back, so then like a 4, and then parentheses x plus 2. Up here, you're taking an x squared, so it's x squared, parentheses x minus 3, and the parentheses were not the same. So there was no way to factor it. So the idea is now, what we have to do is, these are the rest of the roots. So we have to start this whole process again. So we're not going to do the positive negative centroid. We're not going to do that. But I'm going to try to find roots that potentially work on this thing by doing that stupid rule again. And start over. So, we already found one of the numbers that worked, right? What was the one number that worked on this problem so far? -1. So it's got to be one of these 2 rows. Because we already found one of the negative numbers worked. So it's got to be one of these rows. Does that make sense? We've already eliminated 2 of them. Problem is we have to keep going. We have to figure out other numbers that work. So, on that problem, so what am I at? X cubed minus 3x squared plus 4x. Is that a minus 8 or plus 8? Plus 8. All right, so that's where we're at. This is the reduced function, right? We do the exact same rule we just did a little bit ago. We find potential roots by doing that 0 theorem, where you take the back number, you put it over the front number, and you make every combination possible using the factors. So the factors of 8 are 1, 2, 4s, and 8s. The factors of the bottom numbers are 1, and you make every combination possible. 1 over 1, 2 over 1, 4 over 1, and 8 over 1. And these are the numbers I have to check. You have to check all of them again. Don't just throw out one, because what was the number we already did earlier? You have to check that one again, because it might work again. It might be a double root. In fact, it is. So let's plug in a -1. So if we do that synthetic substitution, you can plug in -1 into this problem. Right, so you're doing -1, you're plugging it in, and you eventually find that that is a -1 minus 3 plus 4 plus 8, or minus 4. And this, sure enough, this makes -8 plus 8, which is 0. So yes, that is a root. So -1 worked again. So it was a double root. How many negative numbers were supposed to work on this problem? We just found it. We just found both of them. So those are my two negative numbers that work. It was a double root. Negative 1 worked twice. Now, what should I do now that I know that this negative 1 worked? Synthetic divide it. We have to divide out the negative 1 from this thing. We have to do the whole synthetic division process again. All right, so I'm going to synthetic divide it out because we knew that negative 1 worked. So negative 1, and now that's in the box, and my leading coefficients for that polynomial is 1, negative 3, 4, and 8. And we do that whole thing where we drop down numbers and do that whole process again, right? So we drop down the first number, multiply by the number in the box, drop it down, multiply by the number in the box, drop it down, multiply by the number in the box, and sure enough, it gives me 0. What is this thing now? Yeah, it's whatever's left. It's my remaining roots. 4x squared, 4x, and an 8. This is my remaining two roots. Can we factor that thing apart? I wish it was factorable. It's not. So if it's not factorable, you could do the same rule that we did earlier, where you try all the numbers. Don't do that, because we're down to x squared, right? To find this out, since it's not factorable, do the quadratic equation. So the quadratic equation is negative b. Again, these are my a, b, and c numbers, right? So negative b plus or minus square root b squared minus 4 times a times c all over 2 times a. That's a little sign answer that you had some help for 2. And this explains a lot why it wasn't factorable. Because if I actually simplify this down, 4 plus or minus square root 16 minus 32 all over 2, right? And why is this thing not factorable? They're imaginary roots. Because if you look at that square root, in fact, if I actually simplify this down, that's 4 plus or minus square root of negative 16. This is why you have imaginary roots, because you have the square root of a negative number, which you can't have. In fact, the square root of negative 16, square root of negative 16 is what? 4i? 4 imaginary I? So this is what we have so far for my remaining roots. It's 4 plus or minus 4i, that's the square root of 16, negative 16 over 2. And if I divide both by 2, these are your roots. Those are my roots. They're imaginary. There's 2 of them there. So which row was it? Bottom. This is the bottom row. Watch again. So this is the bottom row. We had 2 negative numbers that worked. It was actually negative 1 repeated twice. It was a double root. And 2 imaginary roots that worked in this problem. So that means when I look at the picture, probably what happened is when you looked at the graph, it bounced off a negative 1 if you're actually doing the graph of this thing, because it was a double root, because that's power 2 on that thing. And then the imaginary means that it would have oscillated up and down, and it wouldn't have crossed the x-axis. All right. Questions, comments about what we did here? Yes.
When you got your second negative 1, you just choose that because you knew it was going to work. Okay.
Yeah, because I just knew for a fact that I've already previously done.
Okay.
So it's just I always stick with 1s and negative 1s. Okay. And you keep trying every number until you find one that works. There had to be another one. And I was trying the negatives because I knew there had to be another one.
And you don't include that negative 1 in your roots because that just tells you which line, it like helps you with which line.
This one?
Yeah.
These are the actual roots. So like if we're listing off all the roots, we have to list them twice. That's it. Yes.
Okay, wait a minute.
Yes.
So like, basically what I did is I just did that because that's what I thought I might have looked at. So I have to go like what's it where unless it's
Okay. Good question. All right. Any other questions that you have? These are good. This is helping us have them done as well. So. Okay. Now that we've done that problem, let's do one of the last ones, because this is like, if you can do this problem by far, like 43 and 44 are the harder problems, because they do this. This is how you had to do them. I think 41, I think what you get in the end, I think it was factorable, I think at some point.
Are we gonna put the work on the homework?
Yes. Okay. All right. So let's talk about one of the last ones, 26 through 32. Even, right? Give me, pick one of them. 30? Okay, let's do 30. All right. So let me explain how this is working. Okay. Good choice on 30, I think.
Yeah.
All right. I think on 30 it said like n is equal to 3, and you had a 5 and a 2, or I think it was like a 5 minus 2i. What is it? I have no idea.
Equals 4 and
Oh, this is a 4?
yeah,
Okay, keep going.
-2, -1/2, and I argue, and f of 1 is
1 equals what?
18.
18? Okay, is that right?
Yep.
Is that just not? Okay. All right. So let me explain this problem and why I chose these. All right. You know how we were doing a bunch of these problems in class, right? We did a bunch of these where I just made up a problem. We tried to figure out the factors and stuff. How I was making those problems up is what you're seeing here. We're going to reverse engineer the problem. I want to go back to the original polynomial. You are given the roots on this problem. You're given the roots. These numbers right here, they even say in the book, these numbers are the roots of your problem. They're the X intercepts. Okay? Even if they're imaginary, they still list them. This is your degree on what your polynomial is going to be. So what will the highest degree be? 4. So we know we're going to have like x to the 4, x cubed, x squared, blah, blah, blah. Right? We'll get back to this thing later. Just ignore this thing for right now. Okay? Just ignore it. Okay, now, when you look in here, how many x intercepts did they give you? 3. There's actually 4. Because imaginaries always come in pairs, plus or minus. Imaginaries always come in pairs. So there's actually 4 roots there. Now, when we looked at like a long time ago, when we were finding roots, like in back in Algebra 2 class, how you find x intercepts, you factor things apart, correct? So if that problem over there, or whatever this problem was factorable, you break it up into parentheses, right? The parentheses on this problem are these. These are the parentheses. Those are your parentheses. Those are all the factors that make this polynomial work. So they're already telling you what this thing is factored out. What I want is what it originally was. So what do you think I'm going to do with all those? Multiply them all together. That's what you have to do. This is how I created your problems in class. I knew what roots I wanted for your problem, and I just multiplied them together. So I knew what my polynomial was in the beginning. So I knew what numbers we should check. Now to do this, we have something weird in the back, right? Imaginary. You always multiply those first if you have imaginary roots, because they should cancel. You never want eyes. So if I go first, outer, inner, last here, this is x squared minus minus negative 1ix, positive 1ix, those cancel, and negative, or positive I times negative I is negative 1i squared, right? 1 times negative 1, and then I squared. Now what is an I squared? That is a negative 1. So what's negative 1 here times negative 1? Positive 1. That's what that parenthesis actually is. So you FOIL first, outer, inner, last. The i's would cancel because I squared is a negative 1, and you take that times negative 1 that was up front of it. And now what we have to do is we have to multiply it on the rest of these. Again, now I know what these things represent. This represents the negative 2. This represents the negative half. This represents the negative I. This represents the positive I. That's how I knew what those roots were. And I'm going to keep FOILing these out until I get down to my polynomial here. So let's FOIL these two together. So this is x squared plus half x plus 2x plus half times 2 is 1. Then if I simplify this out, this turns out to be x squared plus 2.5x, which is basically a mixed number, 2.5 x's. Plus, you can make that a decimal or a mixed number or improper. I might make it improper. That is 5 halves.
Do you think there is a decimal?
You could. Might make it different. Might make it different. Okay. All right. Questions, comments? comments on what I've done so far. Am I done yet? No, we gotta keep going. So now I gotta FOIL that all out, and so what I'm left with is I'm gonna FOIL first, after, and last, x to the 4 plus 1x squared plus 5 halves x cubed plus 5 halves x plus 1x squared plus 1. That's doing this x squared times both, this 5 halves x times both, and the 1 times both. And there should be 6 items there, because there's 3 times 2. All right, now, that is your polynomial. That's your f of x. Now here's the thing. Do you agree that it has the right power on it? Right. We knew it had to be a power 4. There was 4 roots, so it had to be a power 4. Okay, there's even some imaginary roots in there. So we have it. The problem is, we have to make sure that it's giving me this. This thing. This thing has to be correct. This is something that works for your equation. What that means, all this is telling you, is that this is the polynomial. Don't get me wrong. That is the polynomial. But it also could be a multiple of that. It could be some multiple of that equation. Because if I multiply this whole equation by, let's say, like the number 20. If I multiply this whole problem by 20, it still has the same factors. It didn't change it. If I multiply everything by 20, I could have just factored out the 20 in the beginning. And it could have been the exact same roots. They would have the same roots. It would just have a 20 out front. Or maybe this thing was a multiple of, let's say I multiplied everything by 4. So it was 4x to the 4th and 4x squared. And multiplying that by 4, that would be a 10x cubed and a 10x. And then plus 4x squared plus 1, or plus 4. And so I could have factored out 4 right away. And it would still been all the same. It would have been all the same roots. Okay, the 4 would have been up front. Any multiple of an equation is called a linear combination, right? I can multiply any equation by a whole number and it doesn't affect anything. It's still the same equation. It's still be graphed. Still the same. The only difference would be maybe a little bit taller. It stretches it out a little bit. They want to make sure that when you plug these numbers in, it works on that problem. Because it could have been some multiple of this. So this is how we do this problem. How you guarantee to get the correct function. You take your polynomial, and I'm going to plug in the 1, this number right here. I'm going to take my polynomial and plug in a 1 into it, like synthetic substituting it in. Right? So what is this problem? It's a 1x to the 4th plus a 1 squared plus a 5 halves times 1 cubed plus 5 halves times 1 plus 1 times 1 squared plus 1. Right? So that's plugging a 1 in everything. And if this works out, what should this be equal to? This should hopefully equal 18. Now, if it doesn't, probably what happened, they multiplied by some random number. They took this polynomial times some random number, and it made 18. Maybe. I'm hoping it didn't. I'm hoping it's just that, the polynomial. Now, to check, what's 1 to the 4th? 1. 1 squared times 1. 1. 5 halves times 1. 5 halves. 5 halves times 1 is 5 halves. Times 1, or plus 1, plus 1. All right. There you go. That's, simplifying everything down. Hopefully this equals 18. Hopefully they didn't multiply it by anything. Right? These add together to make 10 over 2, because when you add fractions, you add only the top, so the bottom stays the same. So what's 10 divided by 2? 5. So that's 5 when I add those two things together. This is 1 plus 1 plus 1 plus 1. And this turns out to be, 9 when I add those all together. So they, in fact, did multiply by a number. What did they multiply by? 2. They multiplied everything by 2. That means my final answer on this problem, the final polynomial, is taking that whole function, which we just found out. We said, what's going to be correct? They just took everything times 2. And this is why I left it a fraction. Because when I multiply by 2s, it cancels out those fractions. That's why I always like to leave it with fractions. Because I know when I multiply by numbers, it cancels out fractions really easily. Now, if you want to combine like terms, you can do that, but I don't want to do all that. That is your polynomial. That's how I created those problems in class for you. Like when I was asking, okay, let's pick some roots, and then I made up a problem. We did our checks, we did all the synthetic substitution division, we knew what roots were going to work on that problem. I think Kat even made up a problem where you said like 17 was one of the roots. Because I made sure that I did that in my head and multiplied everything else. I'm going to give you the rest of class today. That's about 11 minutes to work on this. Because I know that's rare, right? We haven't seen this. So I want to make sure you get some time to work on that. Okay? When is our homework due? Today. Some point today. I've already done one of them. We only have, I think, 2 or 3 more. Move around. Monday, we'll continue on with this idea of like roots and why I chose these problems, that problem in particular.
Yeah, this is what I have, and I know these are on there, but I didn't realize that we had to make something out. I didn't realize. What do you have to say? I think it's the same one. I really didn't know until I got them. Pretty much like 4 days ago. Okay, so I want to do this. And then we have to find the
I got it, I mean,
So, the good news is,
I got it.
as you can tell, fairly somewhat quick. The only problem that I'm worried about is that. That's the only one that they won't know how to do. They don't have any ideas. The other stuff they've at least done before, they just didn't realize they had to do that one extra step where they can check.
What if it gives you like plus 3i, then you don't do the 2 parentheses because there's that one option? It wouldn't be the negative one too, would it? It would.
Yeah, imaginary is always coming to.
No, you just kind of like add it right here, but you don't repeat. So like 4 divided by 2. That's part of the equation we have to like fill out. So like, and then negative 25. Yeah. That's the one that works. So then you have to do that.
All right. What I can also do, I don't know if it'll be up in time. I could, well, actually, I could do it here. I could process today's pre-calc video. And then decide to play on. So, hopefully I can get through enough where I can get through that first problem. Because I'll be here for like 10 minutes. So hopefully I can at least get started on that first problem. The only problem that would really help me is this one. So, and that, hey, by the way, what problem is that? 30?
we didn't factor it out.
You can still need these.
So,
You want me to leave it up there? You're gonna